Here we're going to go ahead and we're going to try this vertical motion intersection problem. It says, on a lazy summer's day in Chicago, siblings attempt to hit their big brother with water balloons. Little brother is going to drop his balloon from 25 meters above big brother, who's walking on the pavement below. Little sister is positioned 10 meters above little brother. If they release simultaneously, with what velocity must little sister throw her balloon in order for the two balloons to hit big brother simultaneously? So we're going to go ahead and start with that sketch. You know what? I'm going to work on separate paper so I got plenty of room, all right, instead of trying to put things in little blanks. So here we go. So first, let's see here. I got these two siblings up above. So all right. Okay. And it says little brother's dropping his from 25 meters above big brother. So like big brother's down here, right? Okay. And here we go. So going to drop his balloon from there. And again, that's 25 meters above. And this is little brother, big brother. And little sister is 10 meters above little brother. There's little sister. There we go. All right. Now, little brother's going to drop his balloon. She's going to have to throw her balloon down so that they hit simultaneously down here. So I should probably like color code these in some way. That would be useful. So I'm going to do little brother's dropping his. So it'll start still and then go faster and faster and faster as it comes down. Right? And little sister's balloon, water balloon, is going to start, she's going to actually throw hers, so hers starts off moving with some speed. And then going to get faster and faster and faster. And we want them both to hit here at the same time. Alrighty. All right, there we go. All right, so this is an intersection problem. I want both moving objects to be at the same position at the same time, right? They're gonna simultaneously, right? Simultaneously let go and throw them. So the times will be the same for both. So let's see here. I'm gonna start with little brother's balloon. Let's try to color code that in green. So what I'm gonna do, I've got my sketch. I'm gonna go ahead and do a list of variables, right? My motion variables. I'm going to go ahead and make a table of variables for each one. So let's see here. For little brother, you say A, V naught, V, delta xt. Those are my kinematics variables. And I'll do the same thing for little sister. For little brother's balloon, you say, hey, acceleration, when he lets go, the only thing acting on it is gravity. That's the Earth pulling on it, is the only force on it. And that means that acceleration is going to be g downwards, or negative 9.8 meters per second squared. He's dropping it, so that means that starting velocity is 0. I don't know what the speed is when it gets there at the end. Again, we're solving from here to here. But I do know the distance. It's going to go down 25, so it's important that I make that a negative 25 meters for the displacement. Time, don't know. Little sister's balloon, A, V naught, V, displacement, and time. Again, once it leaves her hand, the only thing pushing or pulling on it is the Earth gravitational force, so it's going to be negative g will be the acceleration, negative 9.8 meters per second squared. Starting speed, that's what we're trying to find, how fast she has to throw, so that'll intersect down there. Displacement, it's going to go down 35 meters. And we don't know the time. So when I look at this, now I have my information down. You say, well, I want to write an equation to find this velocity. And you say, but I only have 2 variables. And you say, I remember with the kinematics formulas, there's always 4 variables in a formula, so you have to know 3 of them to solve for the 4th. So I really need a 3rd variable. And that speed at the end there has got nothing to do with little brother's balloon speed. But the times are going to be the same. And so I'm going to use time to link between the two. So that time will be like a third variable I can then solve for V naught. So I'm going to have to get the time from little brother's information. Say, look, I've got 1, 2, 3 variables. I can solve for the fourth. So that's it. That's how this problem is going to work. Is because the way this one's set up, the time when his balloon gets there is the same as the time for her balloon, and then I'll have enough information. Normally, I would go ahead and I would, set up a coordinate axis, and I'd choose a spot to be 0, and I'd be trying to solve for where and when they meet. But this one's different. We already know where they meet. We're just solving when. And I have enough information here. So I don't need to worry about that, about setting the coordinate axis and making sure I'm using a common starting position and a common origin and everything. That's not going to be important for this one, as it turns out. All right, so using this information, you say, I want the formula that's got, I'm going to find t so I can substitute it up there. I've got a v naught delta xt. I want the formula that doesn't have v. That'll be this one. I'm going to write it down here. Delta x is v naught t plus 1/2 at squared. That doesn't have final velocity in it. It's just the 4 variables we're interested in. I want to solve this for t. When I put in my values, I've got -25. He's dropping it, so v naught is 0. Acceleration -9.8. Hey, am I going to have to solve a quadratic here? You say, no, this t term dropped out. I just have the constant term in the t squared. I don't need to use the quadratic, which, not that we can't use the quadratic, but it's always a little bit nicer when you don't have to do that. So I'm just plug that in my calculator. Oops. And I get a time of 2.26 seconds. All right. I'm going to take that time, and I can use it up with this information. So now for little sister, I've got a v naught delta x, and now I have the time. So again, it's going to be that same formula again. We're trying to solve for that v naught. I'm going to use this time from there at 2.26. So I'll go ahead and put that in the calculator. Okay, I got an initial velocity of -4.42 meters per second. All right, and that's it. That's it. That wasn't so bad. That seems pretty straightforward. The way that we gave you the variables there, that was not a bad setup. Yeah. So that's a vertical intersection problem.